it's just a lot of information, but it will condense that down. But on page 381, okay, it's got a table, 13.2, that just lists a lot of the alcohols as you build them up from 1 carbon in length to all the way up to, what do we have, just even 5 carbons. And you'll notice they have a scientific name on the middle column and then a common name on the right-hand side. Now, why that is, I really don't know. With methanol and ethanol, that's pretty much makes sense, but it's a little different when you get to you have propanol, propyl alcohol, and you have 2-propanol, which is probably not used very often. It's probably more so isopropyl alcohol. Why would that be called isopropyl instead of 2? It means the same thing, but where are they getting the isopropyl from? The OH is attached where? In the middle, and that reminds you of what type of derivative? Yeah, an isopropyl. That's right. Okay. Okay. So again, as we're looking at that, so if that's how isopropyl is named, okay, look, for instance, 1, 2, 3 down, the next 3 I should say. Butanol is pretty straightforward. Where are they getting secondary butyl alcohol from just 2-butanol? Yeah, and a lot of these patterns follow the same logic when it comes to just a derivative as opposed to an organic family, it would appear. So then we have 2-methyl-1-propanol, which then reminds you of an isobutyl group, and we had went over that as well. And probably what I would consider the least stable, because for some reason tertiary butyl alcohol, it doesn't have a very good shelf life. I really don't know why that is. It even says it on the bottle that maybe because of its chemical structure, that there would be a logical answer, I do believe. But regardless, it's something with its physical properties on how the molecule actually appears. Okay, so now what I want you to do very quickly is on page 386, okay, it's 13.6, and what it's talking about is the dehydration of alcohols to alkenes. And we had illustrated that, I believe, was that on Wednesday, to where we illustrated the 2 mechanisms, one as a review from last chapter, and then the new one for this chapter, that if you have an alkene and you hydrate it, you're going to get an alcohol. But if you take an alcohol and add sulfuric acid, and that acid is a what type of reagent? It's the opposite of hydration or water, so it would be what? Dehydration. That's right. Okay? So that's what they're illustrating in 13.6. So again, what's happening is you're taking on an alcohol, one OH group off of 1 carbon, and then a hydrogen off another. So that's how we get the idea of dehydration. Okay? And we had gone over some of those reactions that you would see on page 387. The only one we haven't is if you saw one where there was no reaction. So it's called writing equations for the dehydration of alcohols 1. But we want to spend some time on writing equations for dehydration of alcohols 2. And that starts on page 388. Okay. So as we turn the page, okay, and I just want to read this from the top to the bottom. It says the dehydration of many secondary and tertiary alcohols follows a more complicated course than that for primary alcohols. So remember, probably one of the more important things that we said with this chapter was when you're looking at these alcohols, you need to establish what type they are, and there are only three choices. And what are those? That's one, tertiary, and secondary. So that's why it's so important that you recognize those. Most such alcohols have hydrogens attached to carbons on both sides of the carbon holding the OH. Okay? That would be for a secondary and tertiary alcohol. No one would argue that, because when it comes to a primary alcohol, that OH is located where? Like, for instance, on this molecule right up here. How would we change? We know this is a secondary alcohol. No one would argue with that. But how would we change this to a primary alcohol? This end or this end? This one? Well, if we take this carbon off, is that a primary or secondary alcohol? Still a secondary. What if we take this one off? Now it's a primary, okay? So that's what this is referring to, the idea of recognizing those primary and secondary alcohols, okay? Carbon holding the OH will yield two different alkenes on dehydration if the alcohol is asymmetrical. For example, the dehydration of 2-butanol yields both 1-butene and 2-butene by loss of hydrogens from carbon 1 and carbon 3 respectively. Now, it's got a whole lot of information on there, just like this does. It looks confusing, it looks like it's a lot to go over, but it's really not. And we'll explain that here in just a moment. Okay? Dehydration is a selective process. The two alkenes are not formed in equal amounts. 2-butene is the major product. Okay? So what that means, okay, is if that double bond has an opportunity to, let's say, move or be located closer towards the middle, it's going to be more stable. So when that happens, that's going to be the major product every time. Okay? Now that occurs when primary alcohols are located way out here on the end, or excuse me, secondary alcohols. Okay? So what we see here, the relative stabilities of the different alkenes determine which alkene is the major product. The more stable the alkene, the higher its yield in the dehydration reaction. The stability of alkenes follows the order. Okay? And where you see where it says most stable, okay, does everyone see where I'm at on page 388? Where it says most stable, and it's about a third of the way down. It goes from most stable to least stable. And that's what we're illustrating here, okay? So alkenes with more R groups, okay, R or alkyl groups, are more stable for sulfuric acid dehydration reactions, okay? So what it's saying is, for instance, it doesn't tell you that on page 388, but it says R2 carbon, double bond carbon, R2. So what that means is here's your double bonded carbon, and that there's two alkyl groups on this side, and that there's two alkyl groups on this side, okay? That is by far the most stable, okay? And that's what this is trying to tell you down here, that the larger the carbon chain and where that OH is located, whether it's on this one, or this one, this is going to be the most stable. Because notice, as we get lower in carbon numbers, they're starting to become less stable. Now, that's just a chemical property, I would believe, of these types of compounds, that the lower numbers that you get, it just becomes less and less stable. Now, when we apply that to this, it's going to make more sense. So we're almost done here, okay? So stability increases with the degree of substitutions of the double bond. That is, with increasing numbers of alkyl groups attached to the carbons of the double bond. And that's what we're illustrating. That's what that sentence is saying right there. That stability increases with the degree of substitution of the double bond. That is, with increasing numbers of alkyl groups. Okay? So the compound with the most substituted double bond is the major product in the dehydration of 2-butanol. The major product, 2-butene, has a disubstituted double bond, whereas the minor product, 1-butene, has a monosubstituted bond. Okay, now we don't want to go into these cis and trans compounds. Like I said, this just looks like it's confusing, but it's really not. When we start to put that to action here, this is going to make more sense. So I'm going to go ahead and erase this. You didn't need to write all this down. If you did, fine. If not, I should have told you that earlier. Okay, so when we put these to use now, we're looking good time-wise yet. Okay, so when we look at this here, we have this compound here. Okay, I'm going to go ahead and put this on as an OH. Okay, our dehydration reagent, which is sulfuric acid. Okay, so what that means is this is going to have two products. Okay, one of them is going to be more stable than the other. Okay, we can erase this. Because what happens when this dehydrates, we know when that gets stripped off of there, that OH group, it's going to grab something else on this side. So if the OH is coming off, what else do we know is coming off? What atom? Yeah, we're going to take a hydrogen off as well. Okay, so what that means then is, and from prior knowledge, we know that we're going to form a double bond here. So when we say more substituted, it means closer towards the middle. That's how you want to perceive that. Okay? So when this comes off, okay, you look at the left and you look at the right. So when this OH comes off, that double bond can form here, or that double bond can form there. So when that happens, if it's after the first carbon, we know that that is the least substituted compound, making that the minor product. Okay? That's why we're looking at this as major or minor. Okay? So when that comes here, this is less substituted. So therefore, what we would say is that major or minor if it's less substituted. It's the minor product. That's right. This one's minor. And I missed a hydrogen atom here. Okay? So this is the minor product. Okay? So how would we make that a major product? So that rather than that double bond being after the first carbon, who's to say that this hydrogen doesn't come off? Okay? And then when that happens, we've got, I'm going to put that above. Okay? So I intentionally made a mistake. What mistake did we make? Yeah, so we want to put that double bond there. Okay, so once that has happened, we need to take this guy and this guy off. Okay, so what would that, do we have to change anything, or is that right? Yeah, so this and this are gone. That's right. So therefore, when that double bond is closer towards the middle, it's more of a substituted hydrocarbon, making this the what product then? Major product. Okay. All right. Okay. So when we look at this, let's make sense of that. There's two alkyl groups and one alkyl group. Okay? Or excuse me, there's two alkyl groups and two alkyl groups. This one just has one. Therefore, making this more substituted compound, making that the minor, or excuse me, the major product. Okay. Now, when we look at that other compound, we're still good for time. Okay, I'm going to erase this. Okay, so what compound do we have here, just as a quick review? So I thought I had. And I suppose we're going to put this guy on. So what do we have? For octanol. So now we need our dehydration reagent, which is this. Okay. So now, since this, when we said these have major and minor products, that's happening when you're becoming less and less stable. So this, when we had 6 carbons in a chain, that was highly, highly stable. So if we have 8, the solubility, or excuse me, the stability is going to increase. This will not have a major and minor product. Instead, have those that form in equal amounts. Okay? And that, okay, when we look at equations 2, okay, it says look at the carbon atoms, this is that problem, 13.8. Look at the carbon atoms adjacent to the one bonded to the OH. This is just a bigger, it's just a larger molecule. 1, 2, 3, 4, 5, 6. They use 3-hexanol. We're using 4-octanol instead. So we know when this dehydrates, there's going to be 2 compounds. So when this OH gets stripped off of there, what happens after carbon 3 or after carbon 4? When that comes off, it's going to form a what type of organic family? Well, it's dehydrating, yes. But what does it form? An alkene, okay? So what that means is since this compound is so large, okay, and it's got more substitutions, just like what it says, okay, on that, what we read, and had all that information up here, okay, it's the most substituted, so it has 2 products, but they form in equal amounts. Because what it says on the very bottom of page 388, 2-hexene and 3-hexene are formed in equal amounts because each contains a di-substituted double bond. Okay? And what that means is because this is so close towards the middle, that's a di-substituted double bond, but they form in equal amounts. We'll continue with that on Monday. Okay, so look at your papers. What questions did you say you had? I heard 4, 11, and something like that. Okay, so what does 5 look like? How many carbons? Oh, okay. Over here? OH over here? Okay. And that's it? Okay. So, like you had said, propene. So notice if we had propane, it goes to propanol. So if we have propene, it's going to go to propene all. Propene all. Okay? So in this case, this gets the priority because this is the organic family. So we'd already established this. Okay? Now, you're going to say, well, how do we tell the difference between the numbers on there? Well, that's a good question. So this takes priority then, and if we're going that way, that double bond occurs after what? Second one, because we can't do something like this, because remember, if nothing occurs after a number, it's either telling you where the double bond is or where the OH is. So we've got 2-propene. Then, oddly enough, we go way out here to the right-hand side, -1, how do we know it's an alcohol? And how do we name that? OL. Yep. 2-propene-1-all. Okay. This takes place when we have these types of compounds where there's a double bond located. Good question. Okay. And then number 6. Okay. And what does number 6 say? Okay. Oh, yeah. Okay. Down here. It probably says CH3OH, don't it?
It just has like this.
Oh, gotcha. Yeah, so C2OH. Okay. So what's one carbon length in an alcohol? What do we call that? Methanol. So this would be methanol. Then what is this? Yep. Methanol benzene. Okay. Next. Or is that it? Oh, okay. I knew I didn't erase that for a reason. I think that's just luck. Okay, so we have this. So could we give, does this have a common name? Yeah, it does. It does have phenol. That's right. Can we do one of them ortho, meta, para ones? That's correct, we cannot. Why? Because there's more than two. Okay? So this is the most common place. We would say that this is phenol. You'd already established that. No one would argue with that. Okay? So let's just keep it easy and go clockwise. So on number 3 and number 5, we have what? That's what you would, that does make sense, more phenol, but that means we would have to have another compound. But what happens if there's two OH groups on a compound? What do we call that? Diol. So when we do that, we've already accounted for this one. So we just have these to account for, which are on which carbons? 3 and 5. So that means that we've got what? 3, 5. Okay. Phenol-diol. Okay. That's pretty difficult. I would agree. It is. Was that it? Okay. Again, we'll pick up with this on Monday.